In the last lecture, we saw how to reconstruct a signal using a low-pass filter, and in this lecture, we will try to answer a question. According to the question, with practical low-pass filter, can we recover the message signal when omega s is equal to twice of omega m? There are two options, A is true and B is false. So from the question, it is clear that we are using a practical low-pass filter, and in the previous lecture we used an ideal low-pass filter. So instead of ideal low-pass filter, we will use the practical low-pass filter, and therefore we must have the knowledge of frequency response of the practical low-pass filter. And then we need to focus on this condition, omega s is equal to twice of omega m. This means sampling frequency is equal to 2 times the maximum frequency component of the message signal. And we know under this condition, the waveform of s omega will look like this. The spectrums will be touching each other, and this particular condition is known as condition of critical sampling. So we are having the condition of critical sampling, and we are using practical low-pass filter to recover this signal. So let's try to understand if we can recover the signal in this condition or not. In the previous lecture, we saw that the frequency response h omega of a practical low-pass filter will look like this. This frequency here is equal to omega c, which is the cutoff frequency. This frequency here is equal to minus omega c, and from minus omega c to omega c, we call this pass band. And we are calling it pass band because when you apply a signal to a low pass filter, then the signal will be reflected at the output only with the portion between minus omega c to plus omega c. This means the portion of the input signal between these two frequencies is passed by the low pass filter, and therefore we call this pass band. And now we will talk about the stop band. Stop band is the band of frequencies for which the low pass filter we are using will stop the input signal, and it is stopping the input signal because you can see that the frequency response of the low pass filter we are having is equal to 0 when omega is greater than omega c. So we call this band of frequencies stop band, and we are calling it stop band because corresponding to these band of frequencies, the input signal will not appear at the output. That is, it is stopped by the low pass filter. And we know we use low pass filter to recover the message signal. We obtain the sampled signal st after performing the sampling, and then we feed this sample signal to a low pass filter. In our case, we are having the ideal low pass filter. And the output of the low pass filter we call as recovered message signal. So we represent it by MRT. Now this recovered message signal may or may not be equal to the original message signal. There are some conditions which we have discussed in great detail in the previous lecture, and we know the Fourier transform of the input signal st is s omega, and here you can see the Fourier transform, and the low pass filter we are having, which is ideal in nature, is having the frequency response like this. So the ideal low pass filter we are having is having the frequency response like this, and we have the knowledge of s omega and h omega. This means we have the knowledge of input signals Fourier transform and the system's frequency response. So if we multiply them, we will get the output signals Fourier transform mr omega, and if we have mr omega, we can perform the inverse Fourier transform to get mrt. Now this mrt may or may not be equal to the message signal. It depends on various factors. Now let's try to understand whether we can have the recovered signal same as the message signal when there is critical sampling along with the ideal low pass filter used. So we will multiply H omega and S omega, and to give you the clear picture of what actually is happening, I will copy this portion of the waveform and then I will paste it, and finally I will try to overlay it properly here. And now you can see that according to the property of low pass filter, this portion of the waveform of S omega will be passed, and this portion and this portion will be stopped by the low pass filter, and therefore MR omega will have the waveform like this, which is the spectrum of the message signal. The Fourier transform of the message signal is having the waveform like this, as we have seen in the first lecture of the sampling theorem. Therefore here we can see that when omega c is equal to omega m, we know this frequency here is equal to omega m. This is twice of omega m. So here you can see that omega c, the critical frequency, is equal to omega m, and when this happens, we are easily getting our signal back, because mr omega we are getting is same as m omega, and therefore when we recover the message signal, it will be same as the original message signal mt. So I hope this case is clear to you, that what we are required to do when there is ideal low pass filter in the critical sampling case. We are required to keep our critical frequency equal to maximum frequency component of the message signal, and when this happens, we can easily extract our signal back. But the question is asking about the practical low pass filter. It is not asking about the ideal low pass filter. So let's move on to the question. Now we will understand what will happen when there is practical low pass filter in the case of critical sampling. And first we will have a look at the frequency response of the practical low pass filter. The frequency response H omega will look like this, and here you can see that the transition from pass band to stop band is not this sharp. It is taking some time, and therefore here in this case we are having one more band which is known as transition band. From here to here we know it is pass band, and from here to here this portion is known as transition band. So there is transition band, and because of transition band, the stop band will start from here. So this is our stop band, and now we will follow the same process. We will feed our sampled signal to the practical low pass filter, and then we will try to obtain mr omega, and from mr omega we will obtain mrt. So let's quickly copy this portion of the waveform, and we will try to overlay it like we have done in the previous case. And now you can see that, now you can clearly see that this portion of the waveform is passed, which is the spectrum of the message signal, and we need only this portion. But along with this portion and this portion of these two spectrums are also passed by the practical low pass filter, and therefore mr omega will not be equal to m omega, and therefore the obtained or recovered message signal will not be equal to the message signal. So whenever you have the critical sampling case in which omega s is equal to twice of omega m, and you are using a practical low pass filter, then the recovery is not possible. So this is the answer of the question. The answer is false. We cannot recover the message signal when omega s is equal to twice of omega m with a practical low pass filter. So option B is the correct option, which is false. Now there is one homework problem, and in this homework problem you need to tell me with a practical low pass filter, which sampling mode should we use? Option A is critical sampling, option B is undersampling, and option C is oversampling. So try to answer this question, and once you have your answer, post it in comment section. And if there is any condition along with your answer, then also mention that condition. So this is all for this lecture. See you in the next one.